Welcome to Train Signal. You're watching a lesson on random access memory, or what we could simplify by just saying RAM, right? RAM, RAM. And some people will simplify it even further by just saying memory. Now, the concern I have with saying memory is, well, there's different types of memory in a computer system, and so it can get confusing. But more often than not, if somebody just says, how much memory does your computer have? They're talking about how much RAM you have in your computer. Now, I will tell you that RAM is another one of these vitally important components, pretty much a mandatory component in order to make a computer function. Okay, so we've previously learned that we have a motherboard, which is like the heart, and we have the processor, which is like the brains. Okay, so now we have memory, and I don't know what I would analogize this to. It's probably a component of the brain, I suppose. I don't know, but it is something that pretty much is required to make a computer work these days. Now let's talk about the fundamentals of what exactly this RAM is, or what this type of memory is, right? Because I said there were different types of memory. So how does this memory, in this particular type of memory work? Well, the first thing I want you to know about RAM is that it is what's known as temporary memory, or sometimes referred to as volatile memory. Okay, so we have our volatile memory, and then we have our permanent memory. Permanent would be something more like the memory of your hard drive, right? We actually write data to the hard drive, and it's permanently there, or at least mostly permanent. And I say permanent in the sense that it can be deleted, or a hard drive could be damaged, things like that. But as far as the regular functionality of it, it's permanent on a hard drive, whereas when it's in RAM, it's volatile, which means it can only maintain as long as there's power, right? And so here I'm using the example of something called a capacitor, right? So if you know what a capacitor is, these are tiny little components of a system of internal conductors that temporarily store an electrical charge, right? That's what a capacitor is. And that charge, or the data, which is in the form of electrical charge, can be retrieved later when it's needed. And it's interesting because if you've ever actually touched a capacitor, right, you have this electrical energy stored in the capacitor, and if you ever touched it and got a shock, and I'll tell you, it can be quite the shock. Some of these tiny little capacitors can really hold a lot of energy. Well, then you've actually experienced the process of data flow, just the way it does from RAM over to the processor. It stores that data to be released. And when you touched it with your finger, it was released into you. That's why you got a shock. But the one thing you want to keep in mind is that with these capacitors, they eventually lose the stored electrical energy. Okay, that electrical charge that it has, it will lose that eventually. It cannot store it permanently. And one of the analogies that I've heard is it's kind of like a leaky container. Okay, so if you picture, maybe you have a bucket and it's got just a small, tiny little hole in it, tiny leak in it. That's really what a capacitor is like. It actually does have a tiny little leak. So it's not permanent storage, it's only temporary storage. Now, if one capacitor can store an electrical charge, which these charges are like zeros and ones, right? We talked about, I briefly mentioned in the processors lesson, I mentioned about bits of information, and a bit is a 0 or a 1. Well, this is all done with electricity, because electricity can either be in an on or off state, right? And so it's kind of like a 0 or a 1. So if one capacitor can store, an electrical charge, then you can imagine what you could do with more than one, like a collection of them. Well, that's essentially what RAM does. It stores a series of these electrical charges in a group of capacitors. Okay, so it has all these zeros and ones to truly make up the data that we're trying to store. Now on the screen, I have a picture of just, a typical memory chip. Okay, and I don't want you to worry about the chips yet, okay, because they come in these different form factors. That's a term that we heard back in the motherboard lesson. But they come in all sorts of different shapes and sizes. And really, they're all the same shape. Just different sizes and capacities, really, I should say. And we'll talk about that a little bit later. So I don't want you to worry about that. I don't want you to worry so much about what it looks like. I just wanted you to kind of see this is what a memory chip looks like. But I want to tell you, it didn't always look like this. Back in the really, really, really old days, we actually had RAM. We actually had this memory sometimes soldered straight onto the motherboard. Okay, but that obviously posed certain limitations, right? If it was hardwired in, you couldn't expand upon it. And I can also tell you that memory used to be measured in bytes, and then it was in kilobytes. Like I actually remember owning a computer. It was the first computer I owned, and it actually had 1 kilobyte chips. These little cards that we put in. It had these kilobyte cards. So yeah, we used to be in kilobytes, and obviously we moved to megabytes, and now we're talking in gigabytes. But before we get into all of that, I just want you to understand that each RAM module, okay, so each of these little cards here, it has multiple memory chips, and you can kind of see that illustrated. Like you can see these chips. Some of it you can see right on the top there. Each chip is organized into columns and rows. Each chip also has a defined column width, right? So like 8 bits, 16 bits, right? We talked about that before. It's like, right, dealing with the width of the bus, right? We talked about the bus speed and the bus width. Each chip also has a specific number of rows. So you take these rows and columns and you put that together into one of these cells, and that's how it all works. Now, that might not make a whole lot of sense when you look at it this way. So if we look at it this way, when we look at each of these chips and say, hey, we have a certain number of columns and a certain number of rows. Well, the columns and rows is what determines the overall capacity of the RAM chip. Okay, so you picture that we have this grid here, and you can put data into each one of these little cells, right? And the data is these ones or zeros, right? Meaning either it's charged or it's not charged. So first we have this grid determining the capacity of the chip, and then the number of chips we put on the stick itself, on the module, determines the capacity of the overall piece of RAM that you're putting into your computer. Now, as far as a little bit more about how RAM actually works, we have something called DRAM, or dynamic RAM. Well, what happens is the information that is stored in each one of these cells has to go through a process called a memory refresh. Right? So there's these refresh cycles where it goes through and it gets a new charge of information, right? It refreshes the data that's supposed to be in all the cells because it can't stay there very long. Now, RAM, I will also tell you, is, again, it's considered to be the main system memory. That's why when you say how much memory you have in your computer, lots of times we're talking about RAM. It can either be installed on the motherboard, as I mentioned in the old systems, or it can be on chips, which you then insert into a motherboard. Okay, so either way, it needs to be on the motherboard in order to be able to communicate with the processor. The cells are made up of individual capacitors. These capacitors hold temporary electrical charges. Since it's temporary, that means that the charge is going to dissipate. So we have to have this little refresh cycle so that the data is not lost, right? We refresh it, we recharge the energy. And we can do that as long as the computer's on, right? As long as there's power from a power supply. I know we haven't talked about power supplies yet, but that's another lesson. But as long as there's power coming in to the motherboard and the memory's on the motherboard, this stuff can be refreshed. Now, DRAM is not really something that we see too much anymore because the original DRAM operated in an asynchronous manner. Whereas in today's systems, we now have something called SDRAM. And the S stands for synchronous. So we have our synchronous dynamic RAM, right? The DRAM means it's dynamic, right? So we're going through this constant refresh. Synchronous dynamic RAM, or SDRAM, means that it's tied to the system clock just like the CPU. Okay, so basically we have everything working in sync within our system. Okay, so as we're going through cycles of the CPU, we're going through cycles with refreshing memory. And that's where SDRAM comes from. Now, as far as the actual module types themselves, or the RAM sticks, okay, I know, modules is, I guess, the official term, but a lot of people just talk about, having RAM sticks because they kind of look like sticks, right? Now, the original RAM sticks that we had were something called SIMMs, which stood for Single Inline Memory Module. And one of the interesting characteristics of a SIMM is that you had to install them in pairs. Okay? So, back in the old days, when you were buying memory, if there were, let's say, 4 slots, right? 4 slots where you could install RAM on your motherboard, you really only were installing 2 pieces of memory. Okay? Because they had to work together. The pairs had to work together. Okay? And that's about when we had SIMMs. But you'll notice that I have their big obsolete over the picture. We don't see SIMMs anymore. That's kind of the old days. And the SIMMs had to match, by the way. Okay, those 4 slots in the computer, they had to, well, in some cases, all 4 would have to match. And in today's world, we still see some of that where certain things have to match. But we used to have them all matching. But certainly, the pairs had to match. Okay, so you had to have 2 chips that were of the exact same size. And that's why they came in pairs. What we have in today's world is something called DIMMs, D-I-M-M, or Dual Inline Memory Modules. Okay, that's what today's memory sticks, memory modules, memory chips, whatever you want to call them, that's what they're called. They're called DIMMs. Okay, so that's what our SDRAM, and then also we'll talk about in just a moment here, DDR. Okay, DDR2, DDR3. Okay, this stuff all comes in DIMMs. But before we get to that DDR stuff, and I will tell you the DDR stuff is what we most commonly see today, but before we get to that, let's talk about something called the SODIMM, which is the Small Outline Dual Inline Memory Module. And this is the type of DIMM that you would find in a laptop. Now, laptops weren't always this way. Okay, upgrading the amount of memory or adding memory to a laptop used to be a real challenge. Whereas now, they have actually come out with a more simplistic, more universal form factor, and most laptop manufacturers have made fairly easy access to the slots where you would add a SODIMM to upgrade the memory on your laptop. All right, so that's what a SODIMM is. Now, the one below it is an interesting one. There actually is a lot of interesting stuff we could talk about, and we won't talk about everything. But when we have Rambus memory, basically what happened was we needed to find a way to increase capacities and speeds of our SDRAM, because the processing technology, or I should say the processor technology, had gotten to a point where the memory became your bottleneck, and the memory couldn't keep up. And I will tell you that there was a lot of talk about Rambus being the future of memory. Okay? And Rambus is actually the name of a company. Rambus had come up with a design where we basically could now double the throughput on memory, and it was going to be RDRAM, right? So it was Rambus Dynamic RAM. They came on RIMMs, which, by the way, R-I-M-M does not stand for anything. It just rhymes with SIMMs and DIMMs. Okay, so it's Rambus's IM is what it really is. I guess it would be Rambus Inline Memory Module, maybe? I don't know. But anyway, that's what the name of those Rambus sticks were. And I have to tell you, the problem is, and we've seen this in a number of different places in technology, where we think, oh, that's going to be the future of computing. And it had the potential to be. But the problem is that there was a combination of delays in production as well as some significant cost increases. Okay, it was quite expensive to buy Rambus memory. And so basically, it didn't actually take off the way they thought it would be. What did take off, however, and basically because AMD and many of the, I should tell you, part of the reason why they thought Rambus was going to take off is because Intel was behind Rambus, right? And Intel at the time was the primary player in the processor market. Okay, and so they were all behind Rambus. Well, AMD and many other major system and memory makers threw all of their support behind a technology called double data rate, or DDR SDRAM. And you know what this always makes me think of when you talk about Rambus versus DDR? It's almost kind of like if you go back, you have the Sony Betamax versus the VHS or VCR videotape technology, and it was kind of that same thing where Betamax was really where the technology was at. I mean, that was the superior technology, but it was costly and there were delays and it was some proprietary issues and so on and so forth, and so VHS kind of took over as the standard. So DDR is kind of like the VHS. Okay, so that's why I like these kinds of things where you look at history and technology and you look at where you have competing technologies, and it's always interesting who wins and why, right? But in this case, I will tell you that DDR pretty much won out. This is the type of memory that you'll find pretty much everywhere now. Now, DDR actually has 3 flavors, and really it's not as much 3 flavors as much as 3 levels of advancement. Okay, so we have our regular initial DDR. It doubled the data rate. You had 2 instructions that were processed per clock cycle. Okay, and then we had DDR2, which I really need to kind of emphasize, it is not compatible with DDR. If you look at the picture on the screen, you can see that the notch, right? There's a little notch in the bottom of the stick. It is slightly moved over from where the notch is on DDR. And they did that so that you can't put a DDR chip into a motherboard that's designed for DDR2, and you can't put a DDR2 chip in a motherboard that's designed for DDR. Okay, matter of fact, as long as we're mentioning that, notice DDR3 is also not compatible in the sense that the chip gets moved there as well. And I'll tell you what, the bottom line here is you had DDR, which kind of doubled the original SDRAM. You have DDR2 through the use of special buffers, which I guess could be sort of like a cache, essentially doubled DDR. And if that wasn't fast enough, DDR3 could then, again, essentially double the throughput from DDR2. And I will tell you, by the way, some of the advantages, and really I shouldn't say advantages as much as advancements that were made with DDR2 and DDR3 is not just throughput we were getting, but also a reduction in power. Okay, so as far as power consumption, because again, especially with things going portable, and even beyond portability, even if we were talking about a desktop computer, right, we're trying to be green and trying to be efficient with our resources. DDR operates at approximately 2.5 volts, whereas DDR2 operated at 1.8 volts, and DDR3 goes all the way down to 1.5 volts. So we have much more efficient use of power. All right, so now we move into some grids. Okay, and I just want you to kind of take a look at the grid here, and you'll see here that with the original DDR, here I have a series of actual core RAM clock speeds, right? We had DDR 100, as far as 100 megahertz was the speed, all the way down through 300 megahertz. But you'll notice the actual DDR rating was double that, right? So if it was a 100 megahertz core RAM clock speed, the DDR rating, it was actually listed as DDR 200. All right, so if you ever see memory that's listed as DDR 200, you know that it's actually internally a 100 megahertz clock speed that's been doubled. Now from there, we have a PC speed rating. And what this PC speed rating has to do with is the actual amount of throughput. Okay, so what we're basically saying here is if we took that DDR 200 and then we go ahead and multiply that by 8, because that's the width of the DDR SDRAM sticks. So you have the 200 megahertz, right, because that's the DDR 200, that's the speed rating, multiplied by 8, you end up with PC 1600. And what the 1600 represents is megabytes per second. Okay, so that's the actual PC speed rating of how fast the data can travel. Now this might seem like even the slowest one I have listed here, 1.6 gigabytes per second. Wow. You think about internet connectivity, getting 10 megabits, 20 megabits per second, or even how about networking, between computers? You're talking about, if you can get up to a gigabit of throughput per second, between computers, and that's lightning fast. Now imagine 1.6 gigabytes per second happening in memory. Well, remember, for all the data that you're trying to transfer back and forth between computers or out on the internet and this and that, remember how many millions of cycles actually take place inside the system and how much information, how much data needs to go through those cycles in order to actually get the output that you're looking at. Okay, so believe it or not, PC 1600 is not that fast. That's actually pretty much the slowest DDR speed that we're going to get. Okay, because the fastest DDR speed goes all the way up to PC 4800, which is 4.8 gigabytes per second. And again, you think that that would be, plenty fast enough. Getting almost 5 gigabytes per second is really fast. But believe it or not, it's not. Okay? So what they did was, again, through the use of these buffers and the lowering of power consumption, we moved into DDR2. So here's the deal. We start out with our core RAM clock speed of 100 megahertz, just like we had before. The DDR input-output speed is doubled, right? By definition, DDR doubles that, so now we have 200 megahertz. Through the use of these buffers, we essentially are able to double that yet again, and we now go to a DDR2 rating of DDR2 400. Multiply that by 8, you end up with a PC speed rating of PC2, right, to represent that it's DDR2, -3200, ranging all the way on up to PC2 8000. All right, so now we're talking about 8 gigabytes per second with DDR2. But because nothing is ever actually fast enough, we move on to DDR3. And with DDR3 and the advancements in that technology, you'll see here that we now can quadruple the clock speed. So essentially it should be QDR, right? Quadruple data rate. But anyway, DDR3, we're now quadrupling the actual I/O speed. And then through, again, the use of buffers and everything else, we can double it from there to give the DDR3 speed rating, where we end up with a 100 megahertz original core RAM clock speed. Goes all the way up to a speed rating of DDR3-800. Multiply that by the 8 bytes again, and you end up with a PC speed rating of PC3-6400. And look at this. If you get a DDR3-2133, right, that's the chip that you would buy. You go out there and you get that chip. The actual PC speed rating is PC3-17000. Yes, that is 17 gigabytes per second. Is that fast enough for you? Anyway, I don't want you to get too caught up on these numbers. I just wanted to throw the charts up so that you have them. You may get tested on them. And even if you don't get tested on them, if you're ever out shopping for memory, now you have an idea of what these numbers actually mean. Also, keep in mind that when selecting memory for your computer, you can't just decide, oh, okay, this computer supports this one particular rating of memory chip. I'm going to go to a faster one because I want it to be faster. The motherboard and the processor and the memory, everything has to work together. So you need to look at the ratings of this stuff before you buy the computer altogether. Okay, because you can't just buy faster memory. It won't necessarily help you out if the rest of the computer is not designed to support it. Now, when it comes to the reliability of the data, we have these grids, these arrays of ones and zeros. And there's a lot of traffic, a lot of data that's coming in and going out and getting refreshed and all that. Well, isn't there a possibility that there could be some errors, right? Maybe a capacitor is supposed to be on and it's actually off, and things happen. So in an effort to make memory more reliable so that we don't get errors on our computer, right? Especially in the old days, we used to see a lot more errors. We have two different types of memory reliability protection technologies. We have something called parity, and we have something called error correcting code, or ECC. Now, with parity can provide error detection, okay? And I want to emphasize the word detection, okay? Because it can detect the error, but it cannot correct the error, all right? So the way it does this is by RAM storing an extra bit of data per byte. And a byte is 8 bits of data. So for every 8 bits of information, only 7 of them are actually being used for data, and 1 is being used as a parity bit. Now, I'm not going to get into all the mathematical formulas as to how that parity bit is able to determine whether the data is correct or not. There is actually a mathematical formula. There's some exclusive OR type formulas where you can calculate what that parity bit should be, and if you go back and you recalculate and you see the parity bit is not a match, well, then something happened to the data and it's corrupt. It's not accurate. So it can detect the error, but it cannot correct it. Now, not all RAM has parity. Okay, there's parity and there's non-parity. So, when you're purchasing memory and you see something as parity RAM or you see something as non-parity RAM, you understand whether it's got that parity bit or not. So here's the deal. If it's non-parity, it's going to be faster, but it's not going to have that protection built in. Okay, so that's the trade-off that you have to decide. Now, ECC, the error correction code memory, this is the more modern use of memory reliability protection, because not only can it detect the error, but it can also correct the error. And it's capable of identifying these errors bit by bit instead of byte by byte. Because remember, the parity memory can only tell you if the byte of information is bad. With ECC, we now are able to look at the memory bit by bit and determine if there's an error in that bit, and if there is an error, then we can correct the error. Now, here's the deal. ECC is slower than parity. Okay, so if you have parity or non-parity memory, ECC is going to be slower than all of it. ECC is also more expensive. Okay, so again, it's a trade-off. How reliable do you want the memory to be versus how much do you want it to cost, and how much resources do you want to give up on this error correction? You typically are going to find ECC memory on your servers and high-end workstations. Okay, because that's where the reliability ends up meaning more than cost, in some cases performance. When it comes to parity, non-parity, ECC, whatever it is, just like I was just mentioning with making sure you buy the right RAM at the right speed to match the motherboard and the processor that you're working with, well, your motherboard's also going to be rated to support ECC or not. Okay, so you need to understand what type of memory your motherboard supports before you go out and purchase memory. Now, when it comes to the actual installation of RAM, now again, I have another lesson where I demonstrate the building of a computer, but basically, here's that motherboard that we saw way back at the beginning of the motherboards lesson. There's your memory slots that are partially blocked there by the processor fan. Basically, I just want you to notice that they're slots, and these are DIMM slots. So you put one of these DIMM chips in. Before you put it in, you see the little clips on either end? Well, you're going to take those clips and you're going to pop them out. And what you can't really see, but you would if you were looking at a motherboard, is there's a little lever that is down in the slot that kind of pops up when you pop those clips out. You take the memory and you push it straight down into that slot. Now, again, there's a notch. And you can kind of see the notch here in the illustration, but the notch has to line up with the notch on the memory stick itself. So that way you know you have the memory turned the correct way and that you have the right type of memory for that motherboard. But you take the memory and you push it straight down, and when you push it down, it pushes on the little levers inside of the slot, which then make the clips pull in and snap in to hold the memory in place. First of all, it's not that hard to do, and second of all, it'll make a lot more sense when you see me do it in the lesson where we build the computer. All right, so that's how you would do it, and I'll tell you what. Here's an actual kind of illustration of what I'm talking about. Okay, what you're going to do is you're going to push it straight down, and you'll see that you have the notches lining up. And as you push down, these two clips are going to pull in, and then you'll see that the clip also has a little peg that goes into a notch into the sides of the memory stick to hold it into place. And that's how you would install memory. And that does bring us to the end of this lesson on random access memory, or RAM, or some people just say memory, and whatever you want to call it. Just understand it's a very important component. It's a required component. It is fast memory, right? We saw that some of the fastest memory can transmit data at 17 gigabytes per second, but it's volatile memory, Okay, so you can't store things on it permanently. As soon as the computer loses power, those capacitors are also going to lose power, and therefore they're going to lose the data. Okay, so that's what we mean by volatile or temporary memory. But that's pretty much all I have for you. I thank you for watching the lesson, and I will see you in the next one.